Welcome to our help videos, 3B13. This is our unit test. This is the stuff you need to know. If the help videos do not answer your questions, please don't hesitate to ask. Connect with me, email, ask in class, whatever it takes to be sure that you understand these questions. Number one, which of the following statements is false? If we go straight to letter D, we'll see that that is definitely false. Isotopes are atoms of the same element that have different numbers of protons. Well, if atoms have different numbers of protons, they are not atoms of the same element, because what distinguishes an atom as being a particular element is the number of protons. All hydrogen atoms have one proton. All helium atoms have two protons, etc., etc. It's the number of protons that determine which element an atom is. So isotopes are atoms of the same element, therefore they must have the same number of protons, which is the atomic number. What they do have different, though, is numbers of neutrons. Second question. Which of the following statements is false concerning the elements that are captured here from the periodic table of elements? First one, letter A, 195.08 grams of platinum contains the same number of atoms as 207.20 grams of lead. Let's take a look at platinum. 195.08 grams. Well, that's 1 mole. That number is, that 195.08 has two meanings. It is the average mass of the naturally occurring isotopes of platinum in AMUs. In other words, the average mass of a platinum atom is 195.08 AMUs. It is also the mass in grams needed to have 1 mole. So to have 1 mole of platinum, we need 195.08 grams. And 1 mole, as we learned, is 6.02 times 10 to the 23rd atoms. So if we put 195.08 grams of platinum on a balance, we have 1 mole. That would be 6.022 times 10 to the 23rd atoms. Same is true for lead. The average of the lead atoms, if we're looking at the mass of a single atom, it's 207.20 AMUs. But that number has two meanings. It is also the mass needed to have 1 mole of lead. So if we put 207.20 grams of lead on a balance, we would have a mole of lead on the balance, and a mole of lead would have 6.022 times 10 to the 23rd atoms. So letter A is true. They would both contain a mole of atoms. They would both contain 6.022 times 10 to the 23rd atoms. Why does it take more lead, a greater mass of lead, than a greater mass of platinum to have a mole? The answer is because the lead atom is slightly bigger than a platinum atom. So to have a mole of lead atoms, we would need slightly larger mass than we would of platinum. The average atomic mass of gold's right here. The average atomic mass of gold is 196.97, and it says grams there. Wait a minute. Atoms are not massed in grams. Atoms are massed in AMUs. AMUs are based on 1/12 the mass of carbon-12 atom. So that letter B is definitely false. The average of the gold atoms would be in AMUs. It would be 196.97 AMUs, not grams. If we had 196.97 grams of gold, we would have a whole mole of gold. We would have 6.022 times 10 to the 23rd atoms of gold. That is a lot of atoms. That is not the average mass of an atom. That would be the mass of 6.022 times 10 to the 23rd atoms. Letter D, 1 mole of thallium has a mass of 204.38. We come here and we look in thallium square. Yep, 204.38 would be the mass needed to have 1 mole. It's called the molar mass, the mass needed to have 1 mole. So if we put 204.38 grams of thallium on a balance, we would have a mole of thallium. That means we would have 6.022 times 10 to the 23rd. Letter E, a mole of gold has the same number of atoms as a mole of lead. Yep, a mole's a mole. A mole's a mole. A mole is 6022 times 10 to the 23rd, the same way that a dozen is 12. A baker's dozen is 13. A mole of gold would have the same number of atoms, 6022 times 10 to the 23rd. But a mole of lead has greater mass than a mole of gold. Why? Because a lead atom has more mass than a gold atom. Therefore, to have the same number of atoms, we would need more mass. Taking a look at our next question, number 3, and it's referring to these things in the diagram up here. The average mass of xenon. Here's xenon right here. Atomic number 54. All xenon atoms have 54 protons. Now, a lot of people are like, wait a minute, that's where the mass number goes. The mass number is in the upper left-hand corner. Only in nuclear symbol format is the mass number in the upper left-hand corner. On the periodic table, the atomic number, which is this whole number in the squares, can be anywhere on the periodic table. So, what is the average mass of xenon, the atomic mass of xenon? We look in here in the square, it's 131.29, and that is AMUs. When we're talking about masses of atoms, it is always AMUs, not grams. Grams are used for a mole of atoms. That's 6022 times 10 to the 23rd. Number 4, antimony has 2 stable isotopes. Antimony 121, here's antimony square right up here, antimony 121 and antimony 123. 121's mass is 120.90. 123's mass is 122.90. And what they're asking is which of the following statements it is true. Well, 121.76, the number in the square, is the weighted average of the isotopes, in this case 121 and 123. So if we look at 121, its mass is 120.9. If we look at 123, its mass is 122.9. The average of those two, the weighted average is 121.76. So what do we know from that? 121.76 is closer to 120.9 than it is 122.9. It is 1.14 away from 122.9. It is only 0.86 away from 120.9. So what we can conclude here is that it's slightly closer, not a lot closer, but it's slightly closer to the 120.9 number, which means that the 121 isotope of antimony, antimony 121, must be more abundant than the 123. Why? Because the average mass is closer to the mass of 121, which is 120.9. Now, is it dramatically closer? No. So what can we conclude? That 121 must be more abundant than 123 by a small amount, not a large amount. Number 5, tellurium undergoes 2 nuclear changes. And in this case, they're talking about the nucleus capturing electrons out of orbit. And those electrons go into the protons and cause the protons. If a positive particle absorbs a negative particle, the positive and negative become neutral. In other words, the protons change into neutrons. Do we need to really know that that happens to answer the question? Not really. But it is possible if an atom has too many protons and not enough neutrons for the nucleus to be stable, the nucleus can capture some of the electrons that are in orbit, absorb them into the protons. A positive particle and a negative particle become a neutral particle or a neutron. What we do need to know, though, to answer the question, is that tellurium ends up with 2 less protons in the process. So tellurium, right here in this square, starts with 52 protons. If it has 2 less protons, it would now have 50 protons. If it has 50 protons, it would become an atom of 10, letter D. Now, this is not a chemical reaction. Chemical reactions involve changes in electrons. Here, we're having protons change into neutrons. That's a nuclear reaction. So when one atom undergoes a nuclear reaction, it'll end up changing into another atom. In this case, tellurium loses 2 protons. It starts with 52. It ends with 50. It becomes 10. We're going to stop here right now because this video was intended to cover the first page of questions. We'll pick up with the next video on the next page of questions.